Hello and welcome to this very simple tutorial where we will go over the different buckling modes you can have for an unstiffened straight steel column. So here again, very simple, just an erection, meaning just a steel structure and eigenvalue buckling analysis with point loads applied to model a uniform compression on the column, pin and roller supports at both ends of the column. The column is 50 foot long, so it's quite a long column. Okay, so this is by no means a way of saying these are real actual numbers you can expect. You would never have a column that's 50 foot long, especially with the size that we are then providing in this tutorial. Okay, this is just an exercise to prove the efficiency of the eigensolver to find different types of buckling modes. The column is simply supported. We have we can click on this button here. We have a mesh size of 6 inches, a tiny mesh along with 8 elements through the web depth, so that's a really fine mesh. These are the dimensions of the column, and again you see if the unbraced length is 50 feet for this column, it's highly unrealistic. But again, this is not the point of this tutorial. The point of this tutorial is to show you the different types of buckling modes you can expect using the eigensolver that's implemented in Embrace 3D. So we're turning on here the whole length of the girder. We're applying 3-point loads at the ends, so 2 and 8 here. You must have seen this before, mean the top flange and bottom flange node of the section. 50 kips here, so that's really, if you do 50 plus 50, that's 100 kips. Direction 2, meaning that's the longitudinal direction and direction Y here. We are not turning on the self-weight, we're just interested in the effect of the point loads, the uniform compression, and we are defining a search interval from 0 to 50 with a pretty large subspace dimension. Okay, maybe it's quite large here, maybe we could go a little bit lower, maybe to 100, but there's a lot of buckling modes here. That's because it's a huge unbraced length. The column is unstiffened. Okay, we haven't defined any stiffeners on the column, so this is why we initially had a very large subspace dimension, slightly too high probably. We can run the model, but it's actually already run, so let's go to viewer instead. The eigensolver would take a couple of minutes to run. This is the model. Let's decrease the size of the supports and loads. You can see the loads are applying a uniform compression on the column here. And let's look, for example, at the linear elastic solution here. Of course, it's under pure compression, it's just axial deformation here. The first buckling mode here is under 1. So of course, the column, the unbraced length here, it's too long for the column to sustain the load. It will buckle at about 45% of the load price, so at about 45 kips, and that's even without applying an initial imperfection. So the true buckling load is probably slightly less than that. We can increase the scale of this buckling load, and we can then look at different types of buckled shapes. So here we have a mode where we have a double sine curve here between the supports here, but still along the minor axis. Then we can go to a higher mode with 3 waves here, same along the minor axis, and then mode number 4 would be along the major axis bending, okay, major axis of the column at 4.2. This is, again, a theoretical exercise only. We can go to mode number 5, which would be a torsional mode, okay, a torsional mode. We can go to mode number 6 here, which is again a higher torsional mode, and then we can go to even higher modes where then we will switch into local web buckling modes. This should appear pretty shortly. Let's see which mode they appear at. Yeah, so mode number 15 is already a local web buckling mode here. The column is unstiffened. This is highly unrealistic. You would have stiffeners and you would never have a 50-foot unbraced length for this small column. We can even go to higher modes, but I think you got the idea. The idea is that Feast, which is the eigensolver implemented into Embrace 3D, is able to capture any type of buckling mode, and that's something you would not be able to do with beam elements. This is something you can capture only with shell elements. Thank you.